All right, so up to this point, we've been working with a lot of examples that have a numeric continuous response, right? We call these regression problems. Unfortunately, not all problems are like that, and we have talked about the idea of having classification problems, or we may have certain response values that are limited on their range. A good example here is if we wanted to use basically the credit card balance of a customer to determine whether or not they'll default. So we have this plot right here, and we can kind of see that we have a bunch of observations along the x-axis, which shows the balance on the credit card. And then the actual response in this case is yes or no. Will they or will they not default, right? So we have two limited, constrained, specific categories that we're working with. Now, in this case, we could actually revise how we think about this. So rather than just no and yes, what we could say is what we care about is the probability of default, right? So now when we look at this, it becomes a numeric response. However, we're still constrained to the fact that we can't have a probability that is less than 0 or greater than 1. So we still have this, this concept of a limited, constrained output for our response. So one thing that we could do is, well, we could look at linear regression to model this. Unfortunately, when we do linear regression in this case, we can see that our predicted values can actually result in going below 0, right? Or if we looked out further enough, we would see that our regression would predict for greater than probability of 1, right? So problem here is we need to have a constrained value where our response is always predicted between this range, between 0 and 1. So what we could do is we could use this other shaped response variable. And this is exactly what logistic regression is doing. It is modeling this in a way where we will never have less than a 0 probability of default and never greater than a probability of default of greater than 1, right? So we're constraining our response variable. So how does this actually work? Well, if we look at this top algorithm, this is actually what we call the logistic function. It's an S-shaped curve, and you can see we actually have our beta coefficients, right? So we have our intercept here, and we have our predictor variable x here, and we have our coefficient for that with this beta 1. But the algorithm it's a little bit more complex than what we saw before with linear regression. But the benefits of this equation is that it creates this S-shaped curve where we constrain our response values between 0 and 1, the probability of the event occurring or not occurring. Now, there's some nice properties of this algorithm. We could actually rearrange the algorithm a little bit, and we get this second equation that we see down here, and we call this the logit function. And actually what ends up resulting in this case is we can end up getting a very similar equation that we saw with linear regression. The primary difference is how we interpret these coefficients, and we'll talk about that here in a little bit. But the main takeaway here is that logistic regression uses a modified algorithm of linear regression, which creates this S-shaped curve. This S-shaped curve is actually what we see here, this P of X, which is the probability of our event occurring, okay? So in this case, we're talking about the impact that balance has on the probability of default, right? So now our response variable is the probability, which we can see here when we have very low balances. We have a very low probability of default. So our default or probability of default is equal to or close to 0. And as the balance increases, this probability of defaulting increases as well, right? And so that is how logistic regression is modeling this function. It constrains our response variable to be between 0 and 1, and that represents the probability of the event occurring.